Greetings. In this video, we're going to look at column behavior. We will talk about the different stages that columns go through when failing. That's the equilibrium and instability and the loading, column design and column failure modes, as well as very important concept of effective length in column and how the end restraints or how the columns are fixed at their ends affects the column's performance. So columns go through three stages, very similar to the stress-strain curve, where we see when materials are tested and they go from a elastic stage where everything is fine, and then they hit their yield point and some permanent damage happens, and then they finally fracture. In a similar way, kind of analogous, I would say, columns are fine, and then they experience some permanent damage, and then they fail as they move through these three stages. So at the very beginning, stable equilibrium is what we would call elastic behavior. So they are loaded, perhaps a small lateral deflection appears, but once the load is removed, it disappears. So this is normal behavior, expected behavior. Then a column could be loaded and it produces that same deflection, but when the load is removed, the deflection does not disappear, in fact, and it is slightly bent, or its geometry has been compromised. The load at which the neutral equilibrium of a column is reached is called either the critical or buckling load. So this is the permanent damage now. Again, back to my analogy, that would be the yield point in a material. This isn't about materials, this is just about columns, however, but same idea. It's reached its critical or buckling load at that point. And then finally, uncontrollably growing lateral deflections until collapse. So this is the end. This is the fracture. Okay, so those are the three stages. Slenderness is an important point or concept that structural engineers are concerned with. So slenderness is the ratio of the unbraced length to the least side dimension. So two things are being compared here, or turned into a ratio. The unbraced length and the least side dimension. So the unbraced length, the height, is often the overall height of a column. That is true. If there's no brace, then the unbraced height is the overall vertical length of the column. This column right here, however, the unbraced length would be the LAW, LY. And that is because this is the distance right here from the top of the column to the bracing, or same distance. This one's equal in thirds. So that's why they could take any of these numbers, basically. So this is the unbraced length here from the end of the column to its next brace. And the least side dimension would be the thinner of the two sides. So if a column is a 4x6, then the least side dimension is the 4 inches. So 4 inch by 6 inch cross section. So we could see, like here, for instance, let's say this is the 4x6, then the least side dimension would be the 4 inches. Okay. So here we see the columns. So here are some common braces. So if this is a 10-foot tall column and this brace is coming down at 8 feet, for instance, then or this up 8 feet from the ground, and this is the top 2 feet, then the unbraced length is the 8 feet, actually. This column right here, pretend it's 20 feet, then the unbraced length would be the 10 feet, because this is coming in at the midpoint there. Okay, a couple different ways that columns fail. Torsional buckling, lateral buckling, and compression. And that's what we see here, these three. So torsional buckling, we see this type of a twisting occurring. So this must have been a seismic event, an earthquake that occurred. Lateral buckling or bending, that's here. So lateral is coming in from the side, right? This is the primary axis of the column, and columns are loaded with their axis, in line with their axis, and then the lateral is coming in from, lateral refers to sideways, essentially. So it's moving to the side, buckling or bending. perpendicular to that axis. And then compression is here. That's where it's actually getting crushed. So 3 different ways that a column could fail. Here we see the torsional buckling again. So a column with a cross section that lacks symmetry may suffer, or is more prone to suffer from this torsional buckling as well. Here we could see a column in plan, and what we're seeing actually is a column. We've cut through the column and we're looking at its cross section, and this is the part that we cut through here. This is the part with the hatch, and then this column is actually must be probably on an incline. Actually, I think it's wider at its base, shorter at its top, perhaps one straight edge, and then the other edge, the other face of the column is on an incline. That's why we see this part here that has not been cut through. So what that's telling us, in the same story here, we've cut through this column at this point, but there's additional kind of geometry down there below that we haven't cut through. So what that's telling me is that the center here of this area is not really a straight line. The center of the column is not a straight line because it is wider at its base than its top. And therefore, it is, again, prone to torsional buckling. It is not a symmetrical column. Wider at the base, shorter at the top. All right, a short column under the action of an axial load will fail in direct compression before it buckles, but a long column loaded in the same manner will fail by buckling. So here's a twisted column, tall, slender column, and it's beginning to buckle. We see that happening right there. And I think this is very intuitive. That's what you would expect when a tall, slender column is loaded. Here's a very short column, and again, I think it's intuitive. You would not see such a small column up here, you could call it, buckling in this manner. This would get crushed first. And then intermediate length columns might fail by a combination of the two. So crushing and buckling. Tall columns, shorter columns. Okay, the centroidal axis is the line joining the centroid of each cross section along the length of the axial member. So again, here's a nice square column, and then this is the centroid, up and down. So I would tend to believe that this column is square with these dimensions top to bottom, and then the center point never changes. However, back to this example, again, the base of this column is bigger. That's what this space is suggesting to me. And therefore, the axial, the line of the axis there is eccentric. It's eccentric because it is not straight. Or if you had a timber column, for instance, it could be an imperfection that does this. It could be a crooked timber. And when this load is not perfectly centered, when the loading does not run straight down the center or agree with the center of the column, then it is eccentric. And if it is not concentric, but it is eccentric, then that line of action is not precisely in line with the center of the axis. So that load is moving off center from the column, basically, off center. And it subjects it to immediate bending. That's what's happening here, I believe. And of course, structural engineers just have to contend with this issue. It's not impossible, but it just has to be addressed. And we could actually see that here, where the loading would not be concentric. So here we see a parking garage column. It is under construction, so right now this column is only loaded from one side, and that again will create that eccentrically loaded condition. And all columns on the perimeter of a building would, of course, be eccentrically loaded because the floor is on one side and nothing is loading it from the other side. So all peripheral columns are eccentrically loaded. Okay, now getting to the issue of column restraint at the ends. How do we secure our columns? So they could be pinned. They could be fixed, and we learned about this all in earlier on in the course. the different types of end restraints or connections. We were talking about connections at that point, but it's the same thing. Or free. So this looks like lights or something, maybe at a stadium or something. So completely free at the top. Nothing is restraining it there. So these are the three options: pinned, fixed, and free. So this is like the flagpole, essentially. Here we see a fixed or restrained column connection. So this column top would not be allowed to move in any direction. Here we see some attractive pinned columns. These being the columns, and these are the pins, or the hinges. And how does this affect? So this is a very important concept. We'll look at it in a couple of slides. So here is the diagram. Let's talk about that first. So right here is the floor, right across the bottom. Here is the ceiling, or the top of the column, right across the top. So we have 4 columns, 1, 2, 3, and 4. Here, this is telling us that the effective length equals L for this column, and that is that height from the top to the bottom, and the effective length is called L. And here, both ends are pinned, and that is kind of the benchmark, because L is just L. However, if we fix both ends, and that's what this hatching, and this is a common symbol for a fixed end. So here we have the bottom is fixed, so those little circles are the pins. So here, fixed top and bottom, and that is a more rigid connection, so therefore the effective length equals 0.5 L. So it is half. So this column, because of those end restraints, has an effective length that is half of this column. So that will improve its performance. And then here we have pinned at the top and fixed at the bottom, and the effective length, not surprisingly, falls between these two with a multiplying factor of 0.7. And then here we have the flagpole fixed at the top, fixed at the bottom, and free at the top, and not surprisingly, with this complete lack of restraint, the effective length is the greatest, 2 times L. So if this were 10, the effective length were 10 here, it would be 5 here, which is the best case scenario. It would be 7 here, and it would be 20 here. So best, second best, third best, fourth best, or least desirable. The column's effective length corresponds to the distance between the points of inflection or bending when buckling. That's what these dashed lines are showing us. The smaller the effective length of a particular column, the smaller its danger of lateral buckling, and greater its load carrying capacity. And it's determined, as we just discussed, by its end restraints. And this is just kind of blowing that up so you could see it more closely. And here's an interesting test with the same, essentially. So this model shows the boundary conditions, or the end restraints, how they affect the critical load of the column. Notice that each of the columns are identical apart from the boundary conditions. So our columns are all the same material, and we see the deflection from, so this unloaded. An unloaded column would be all the way over here, straight up and down, and then it was loaded and it deflected X amount. And they look like they've all been taken, or these three at least have all been taken to the same point of deflection. The same amount of deflection has occurred. And so kind of different from the chart before, this one is showing us actually with weight that while accomplishing the same amount of deflection, the fixed and the fixed carries a lot more load than the others, apparently. Fixed and pinned, the second greatest amount of load, and pinned, the third greatest amount of load, all with the same amount of deflection. And fixed comes in 4th place, and we could see just how far that moved, actually. It moved a lot more than those. It deflected a far greater amount than these three with the least amount of load. So not a very stable column there. Okay. All right, and then we will finish with it, looking at a couple of charts, how to determine some load carrying capacities of columns. So the design of columns, or the design of any structural member for that matter, is complicated and repetitious, the process. the allowable stress for a column is dependent upon the actual column dimensions, which aren't known at the beginning of a design process. So that's why it's repetitious. There's a lot of back and forth. So a trial and error process is therefore required. And sometimes designers, both structural engineers and architects, will use tables and graphs to kind of get us started down that road of design before doing actual formulas. Just so these charts are really just starting points. So here we have the nominal size of the column in cross section. So that would be a 4x4 column. So this is the cross section again. The length is coming across the x-axis at the top, cross section on the y-axis, and then in the field here we have how much load the columns will hold. So the smallest number on the chart is, and this is all in kips right here, 1,000 pounds for kips, okay? And then this is also all standard for wooden columns, Doug fir. So the smallest load carrying capacity on the chart is here, 2.63 kips, and not surprisingly, it is the smallest cross section at its tallest height, basically. You can't use a 4x4 column above 14 feet. It would fail. That's probably why there are no numbers here. So this is the most slender column at its tallest carrying ability. Okay. And here we have a 6-footer that could carry 11 kips. So a much shorter column has much greater load carrying capacity. And then the biggest number on the chart is right here, 238 kips. So a very heavy, carrying a very, very large load. And that is a timber that is 16 by 16, so a very, very big cross section. And at only 6 feet, it has its greatest carrying capacity. And then the taller it gets, the load carrying capacity diminishes. Okay? So 3 factors, and on a quiz you would get 2 of them, and you'd have to find the third. And if we look at this example, so recommend the most economical member. That's economical. When we talk in structures, that's not really about price. It means the smallest member, and that is completely fine to take the most economical member, because there are a lot of safeguards built into engineering formulas in both on the structural side and of course with codes. So there are safety factors built in on the structural side, and that's why it's taking the most economical member doesn't mean that you are being cheap or compromising safety. That's all taken care of within the codes and the formulas. So the most economical member that will support 30 kips and has an unbraced length of 9/6. The answer is 6x4. So we would start with the unbraced length of 9/6, which falls right here between 8 and 10. So very important, you must round up, right? If you round down, you are being too liberal, and you are saying that the column is shorter than it is, and expect to perform better than it would. Okay, so you want to round up and be conservative with this one. And then we have 30 kips. So we located our unbraced length, and we are looking for 30 kips. So we will come down. 28.5 does not cut it, so 36.1 kips is the first that satisfies what we're looking for. And then we come across here and we see that the answer is a 6x10 column. Okay, and let's look at one more. So again, how many kips can a column support with an unbraced length of 15 and it has an 8x12 cross section? So we take the 15, we round up to 16, and then the 8x12 is here, and then we connect the dots and we find that it could support 49.6 kips. Okay? All right. Thank you. I hope you enjoyed that.